Sorry for that one. I thought we still have 30 seconds, more or less. Anyway, so do you guys have a question so far? Or is there any other people who has a question? So another technique here is your goal should be only focusing on the conclusion. So just find a way to prove that these hypotheses are really equal with this conclusion. Okay, by applying, of course, the inference rule or the equivalence logic. Okay, so you can have a longer solution but come up with the same result, which is the conclusion, and you can actually come up with shorter solution but still come up with the same result. Then that's okay, as long as we have the same answer. It's just that we have different approach. So do you guys have a question before we proceed to the next one? Or do you guys need more time to analyze this one? And also, I guess the other tip or technique that you may apply here is practice. Okay, just need to familiarize yourself on how to solve such things. Okay, so you can find other examples on the internet and then try to, compare your answers versus the answers of the internet. Because again, we can have different solutions but the same answer. All right, so since we can afford to stay here for 5 more minutes, so I'll just leave this one to you guys as your self-study or self-verification study. Okay, if you cannot really understood what happening here. Right, so it's practice, practice, and practice. So once you're done in doing your practice and then familiarizing everything, then you can now proceed and answer this secret. Okay, so this is another secret wherein you're going to write a proof of sequence for the assertion. So we have this inference format, and then we have the other expression wherein it's not in inference format. So in here, no problem, just the same with our past examples. But for number 5 and 6, so you have to convert this one first into an inference format. And then from there, you can now proceed with the solution, just like this. And then in answering this one, since I think it's doable in Microsoft Word, but it's super difficult, okay, especially having this kind of bracket. I wasn't actually able to find this kind of bracket. We have the other way around, but yeah, that's a different bracket. So I will let you guys do this one using handwritten. Okay, solve this one using handwritten, but please write legibly and then take a picture of your solution and then your final answer clearly. Okay, so it should be clear, not pixelated. Okay, so there should be also a good lighting, a background light, so that I can see your solutions clearly. Okay. So yeah, that's it for your secret. Do you guys have any concern or clarification regarding with your secret?
None, sir.
How about the others? Any clarification? Or concern?
None, sir.
None, sir.
Wala po.
All right then. Okay, the next one is Modus Badus, just like what I have said a while ago. Okay, so if you didn't follow the inference rule properly, you'll come up with a modus badus result. So just like this one. Okay, so P conditional Q, and then we have proven that Q is actually true. This one is actually, no. In here, actually this one, the result should be Q. Okay, so we don't have rules wherein we're going to answer letter P. So the only way that we're going to answer letter P or the hypothesis is if this one is a modus tollens. And then for us to be able to say that this one is a modus tollens, if we have proven that the conclusion is actually false. But in here, they are both true. So as you can see, this one is incorrect as your conclusion. So if ever that you're going to verify this one using a truth table, this one is actually not a tautology. So if it's not a tautology, then this one is called already modus badus, not a valid rule. Okay, so the same with this one. Okay, if ever you're going to come up with a truth table of this one. Okay, and then the same with this one. Having this kind of expression, so if we're going to analyze this one, so we have proven that P is actually false. However, if this one is true or false, we will still answer letter Q as it is. We will not change the truth value of this one, or we will not apply a negation. So that is why this one is also incorrect way of solving inferencing rule. So as you can see, if you're going to solve this one or construct a truth table from this one, you'll come up with this kind of result, and then there is one false on the truth table or the result. So this one is not a tautology also. So we call this one modus badus also. All right. So yeah, that's it for the modus badus. And then the next one is mathematical induction. So this one is a method of proving a formula wherein I think I wasn't able to put all of the definition. Anyway, so this is a method of proving a formula from long or from expanded formula into another formula, which is of course a fixed formula, wherein instead of writing a longer or expanded formula, if we can come up with deduce or a smaller or shorter formula, then we will just follow, of course, the smaller one. So in here, we will try to prove that one using mathematical induction. So we have here the principles or two basic principles. So step one is by replacing the formulas or the variables by one. And then you have to prove that they are true in terms of equivalence. So the left expression and then the right expression. After that, once you have proven that they are true after replacing the variable by one, then you can now proceed to step number two, which is called the inductive step. So if S1 is true for all, I is less than n plus 1, then S, n plus 1 should be also true. Okay. So in here, instead of just replacing the variable by 1, we will now go and replace the variable by n plus 1. So in here, we're just making the expression a little bit more difficult. And then it should be also true since we didn't change anything. It's just that we've just changed that variable by n plus 1. So for you to be able to appreciate this one, so what are those steps? What are you trying to say, sir? So we do have example here, okay? So we have to show that this expression, 1 plus 2 plus 3 plus up to the infinity, okay, is equal to this kind of expression or formula, okay? So again, instead of writing 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus up to infinity, so if you can come up with one formula wherein this one is equal with this one, then why not, right? So we have here the solution. So we have to prove that this left expression is equal to your right expression, okay? So step number one. So just replace the variable by 1 or let n equal to 1. So just copy the letter n on the left side and then the entire expression on the right side. So just replace this one into 1 and then the n into 1, n into 1, and then simplified it. So as you can see right here, of course, simplify the parenthesis first. 1 plus 1 is equal to 2, and then 2 times 1 is 2, and then 2 divided by 2 is equal to 1. So in here, we have proven that this right expression is equal to your left expression if you replace the n by 1. Okay. However, if you really wanted to verify this one, whether this one is really correct, okay, or really equal with your left expression, you have to do this step number 2, wherein instead of just replacing, okay, the n by 1, you have to replace now this n by n plus 1. Okay. So again, we're not trying to change anything in here because whatever you're going to apply on the right side will be applied onto the left side. Okay. So from here, we have to show that, for example, just copy this one for now. Right side expression, n times n plus 1 divided by 2. Okay. And then replace them, or replace the n by n plus 1. Okay. And then this is now the replace or the updated, okay, steps. And then just simplify this one, and then you will come up with this kind of expression. N plus 1 times n plus 2 divided by 2. Okay. So now we have to show that this expression is equal on the left side expression. Okay. So how do we do that? So we're going to change the approach. So from here, just get this one, or we have to show that this one is equal to this one if we're going to add n plus 1 to the original expression that you have on the right side, and then the original expression on the left side. Okay, so our goal here is to come up with the same expression. Okay, if we're going to add n plus 1 on the right side, which is this one is the original, and then n plus 1 on the left side also, which is this is also the original. Right? So from here we could simplify this one into this. So how did we come up with this one? So again, in combining two expression, so just cross multiply this one. So 2 times n plus 1, and then the denominator of this one is 1. So 1 times n plus 1. And then whatever is the denominator of those two expressions, so just multiply it. So 2 times 1 is 2. So that's how we come up with this result. Okay. So were you guys able to follow up to this point?
Yes, sir.
Or quite confused?
Yes, sir.
Okay. So I bet that 80% you are quite confused if this is your first time. Okay. If ever that this is your first time learning about mathematical induction, okay, 80% you might be confused or lost right now. So you don't know what we are trying to do. Okay, so I highly suggest that once we're done with these basic examples, try to look on the other examples on the YouTube. Okay, so we have the same steps. Step 1, replace the n by 1. Step 2, replace the n by n plus 1, and we prove that form n plus 1 is really equal with your original expression if you're going to add n plus 1 on that one. Anyway, from here, there's actually so from here we are now saying that this one is equal to this expression, right? So maybe if you're going to analyze this one logically, okay, or with the use of your mind only, it's quite difficult. So that is why I'm going to show to you guys on how we've come up with such result. There you go. All right. And then let's change the size. So from here to here. So who were able to get this one? on how we've transformed this expression into this one. Is there anyone who's confused? Or it's okay?
It's okay, sir.
What is that? So
It's okay, sir.
I would say that it is not my problem anymore because you are already done with your algebra. So I'm really hoping that you guys already know how to, add certain variables, okay, into a single variable, or a single expression. So again, from here, we just cross multiply. So 2 times n plus 1, and then 1 times n plus 1, which is now equal with this one. Okay, then the next one, so we're trying to say that this one is also equal with this one. Okay, so how did we do that? So first is you have to expand this one. So n times n times 1. So just expand or distribute that one. So n squared plus n plus 2 times n, which is 2n, and then 2 times 1 is 2. Okay, divided by 2. So just simplify this one a little bit more. So n squared plus, so since we have the same variable here, so we can combine those two. So n plus 2n is equal to 3n plus 2. Okay, divided by 2. And then from here, if you're going to expand this n plus 1, n plus 2, this one is actually equal with this one. Okay, so let's see if they are really equal. N plus 1, all right, so we'll not show that one. So we'll just do the FOIL method. Okay. N times n is n squared. And then n times 2 is 2n, so plus 2n. And then 1 times n is n. And then 1 times 2 is 2. So simplify this one. So n squared plus 2n plus n is equal to 3n. And then plus 2. Divided by 2. So that is why this expression is equal with this expression. So they are the same. Were you guys able to follow?
Yes, sir.
Yes, sir.
All right, that's good. So now we have now proven that this, this expression just by adding plus n plus 1 is really equal with this result that we have a while ago. All right, so that's mathematical induction, okay? Proving that this right side expression is really equal with your left side expression if you will come up with a different approach, like having this one n plus 1. Okay. Then we have here another example. So show that if r is not equal to 1, then a plus a r raised to 1 plus a r raised to 2 plus and so on and so forth, wherein it's also incrementing by 1. So wherein we could say that this expression is actually equal with this one. Okay. So since we are dealing with call this one exponent, so we should start with 0. Okay. Why 0? Because if you're going to put there 1, then you're trying to neglect the first step already. So we have to start with 0 because any number that is raised to 0 is always equal to 1. Okay. So in here, just get the left side expression wherein this one, AR raised to n, and then just get the entire right expression. And then replace the n by 0. So the n became 0, n became 0, and then just simplify this one. Okay. So 0 plus 1 is 1, which is now this one. So a times r raised to 1 minus 1 divided by r minus 1. And then any number that is raised to 0 is 1. So that is why we have this 1 here. And then just simplify this one more. So a times 1 is a. And then in here, you can actually cancel this one out. So r raised to 1 is the same with this one. So we'll just cancel that one out, which is now equal to a. So from here, we have proven from step number 1 that this right side expression is really equal with your left side expression. Okay. So of course, we are not yet done. So we have to proceed on the step number 2. We're in making the n into n plus 1. Okay. So we have to show that just by replacing this 1 into n plus 1, we have to show that we can come up with the same result. So I didn't show the step-by-step solution anymore on how we come up with this one, but just by replacing the n into n plus 1, so this one will become n plus 1 plus 1. So from here, we can actually simplify that 1 into n plus 2, which is now this one. So you can actually do that one mentally, so that is why I didn't show the step-by-step solution anymore. Anyway, so how about if we're going to add n plus 1 or ar n plus 1 on the right side and then ar raised to n plus 1 on the left side. So we have to prove that this right side is still equal with this expression. So from here, again, just cross multiply this one. So r minus 1 times ar raised to n plus 1. And then 1, so we have here an invisible denominator, which is 1. So 1 times a times r raised to n plus 1 minus 1 is now this one. And then just multiply the denominators on both sides. So r minus 1 times 1 is r minus 1. So from here, this one now, if ever you're going to simplify this one a little bit more, this one is actually equal now with this one. So from here, we now have proven that this right side expression is really equal with the previous right side expression that we've got. Okay. So yeah, in mathematical induction, this one is actually a lot of practice. You'll need a lot of practice for you to be able to appreciate or master this one. But for now, were you guys able to follow this step-by-step solution and how we've come up with this final result?
Medyo.
Okay. So from here, just try this one more. So on what part or on what topic of Module 3 you've had a hard time in trying to understand? Is that the inferencing rule? Is it the proofing? Or the mathematical induction? None. So I'm hearing no one. So no one's responding. So meaning, lahat mahirap. All of the above are difficult. Am I correct?
Yes, sir.
Yes, sir. Yes,
Yes,
sir.
sir.
So maybe mathematical induction is yes 100% difficult. So highly suggest you guys to explore more on the internet or other examples on how we've come up with a certain result. And then for the inference format, so this one is actually easy, but needs familiarization. Okay. And then what else? For negation, I guess no problem with this one. This one is super easy. And then identifying this one, whether this one is true or false. So very easy also. Okay. So let's practice more when it comes to mathematical induction and inferencing format or inferencing rule. Okay. So again, after you're done in understanding what is mathematical induction, so try to answer this seat rate. So don't worry, I only gave 2 seat rate. So prove that this expression is really equal with this expression just by doing these steps of mathematical induction. The same with this one. Okay. Right expression should be also equal with your left side expression. All right, so that's it for the module 1 part 3. So we are now actually done with the module 1. So we will now start our module 2 next meeting. So before we end this meeting for the day, do you guys have any other concern other than the mathematical induction?
None, sir.
How about the others? Any concern or clarification?
Wala naman po, sir.
None, sir.
Okay, so again, in answering this one, okay, so answer this one handwritten. Okay, so, but then again, you must write legibly so that I can understand your handwritten. So I can check it properly, because if I cannot understand it, then I just might mark it incorrect or wrong. Okay. So just write legibly and then take a picture of it clearly, okay, before uploading that one on our canvas. All right, so if you guys do not have a question anymore, so you guys may now go, and then good afternoon to all of you again.
Yes, sir.
Bye, sir.
Goodbye, and then thank you for coming.
Bye, thank you, sir.
Goodbye.
Thank you, sir. Bye, sir.
Thank you to.
Bye, sir.
Goodbye. How about you, Mr. Janeza and Mr. Rava? Do you guys have a question?
Wala na po, sir. Okay na.
Okay, so I'm ending this meeting now. So goodbye, and then see you guys next meeting.